Okay, first, I would like to thank the organizers to give me such a chance, especially Professor Adrian Constantine. And it is my pleasure to give such a talk, dynamics near a shear flow with Coriolis force. So we first consider the two-dimensional incompressible Euler equation with rotation. After the beta plane approximation, the Euler equation takes this form. So this is the two-dimensional velocity, and this is the pressure. Beta is a real number, and G, here G is the standard 2x2 symplectic matrix. So the region is a channel. On the in the x direction it is periodic, and in the y direction it is there are two fixed boundary. On the fixed boundary, the condition is given by the second component varnish. If we take curve of the velocity, we get the vorticity, and by the incompressible condition, we can define a stream function in this way. So the Euler equation can be written in the form of vorticity. A shear flow means that the first component of the velocity is uy, a function of y, and the second one is 0. It is a steady state of the Euler equation. So this talk is mainly to study the dynamics near such a shear flow. If we first linearize the Euler equation near the shear flow, we will get the linearized equation. And we mainly focus on the following three topics. The first one is the linear stability, instability. It mainly considers the spectrum of the linearized operator. This is a linearized operator. Mainly it is in the mathematical way. If the spectrum of the linearized operator on the left hand side of the imaginary axis, or exactly on the imaginary axis, then we call it spectrally stable, or sometimes the linear stable. And if we can find so the linear instability is always means we can find such an eigenvalue which is in the right hand side of the imaginary axis, and then we will get an exponentially growing solution of the linearized equation. The second is nonlinear stability, instability in the sense of Lyapunov. This, I think, all of us familiar with this. And the last one is the long-term dynamics. The long-term dynamics mainly studies the asymptotic behavior at time go to infinity. So if we see, if we first consider the shear flow, there is a family of shear flow near the given shear flow, right? And if there are other non-shear states, then the dynamics, the long-term dynamics may be complex, because as the initial data from, is near the shear flow. And if the shear flow is in the sense of is nonlinearly stable in the sense of left node, then as time goes to infinity, it might convert to the non-shear steady state. So this gives richer long-term dynamics. And maybe there are some traveling waves. So let us first see the linear stability instability. A method is called the normal mode method. We take such a solution in this form into the linearized equation, and then we get the really good equation with the boundary condition, with the Dirichlet boundary condition. So the shear flow is linearly unstable if one can find such a non-trivial solution to the system 5 and 6 with C. Here C, the imaginary part is positive. If the imaginary part is positive, then we put it into the solution, we will get an exponentially growing solution, right? So first we recall some history of the linear instability. These three results mainly gives the necessary condition for the linear instability. The first one is due to Rayleigh. So it is sometimes called the inflection point theorem. It means that if there is an unstable eigenvalue, then the second derivative of the profile U will change sign. Extended it into the beta plane case. I mean, beta is not zero. The second one is the Harvard semicircle theorem. It gives a reading such that the unstable eigenvalue lasts in. So if beta is zero, then the semicircle theorem says that the unstable eigenvalue must lie in such a semicircle. Here Ci is positive. And Pilowsky extended it to the case of beta is not zero. And here the radius is somewhat larger. It depends on the parameter beta and alpha. Here alpha is the wave number. And Miles, Pilowsky, they further extend the result. If beta is positive, then there is no non-trivial solutions if for C. For the real part of C is larger than the maximum of U. And if beta is negative, there is similar results. So the story of the linear instability is always the necessary one. So next we give some sufficient condition. For the sufficient condition to ensure the linear instability, for general shear flow, it is very difficult. So we now consider a special class. Here we call it class K plus. What does it mean? It mainly means that for any beta is in the range of the second derivative of U, then one can find such a U beta. It is in the range of U, such that this guy is positive and bounded. So the point is that generally speaking, if U beta is in the range of U, then there is singularity here. But this condition means that it is bounded. Means what? Means the singularity can be cancelled. And furthermore, it should be positive. There is some restriction of such flow. So I said this is a spectral class of shear flow. For example, the standard flow, it satisfies this. If beta is 0, then and you belong to this class, the shear flow belongs to this class. Now let us now let the minus alpha max square is negative to be the principal eigenvalue of the Sturm-Liouville operator. Then there is a sharp condition for the linear stability. It says that if alpha is a Biot number, it belongs to 0 and alpha max, then there is instability, linear instability. If alpha is larger than alpha max, larger than or equal to alpha max, then it is the shear flow is linear stability. And beta is in the first equation. It is yeah. It is due to the Coriolis force. In the case of beta is not 0. Actually, Guo has numerically found the unstable eigenvalue mainly lies in the region 1, region I, in this region. So we analytically prove that the unstable for alpha, beta is the Biot number, beta is the Coriolis parameter. The region I is if alpha beta is in the region I, then the linearized operator has an unstable eigenvalue. So if beta is 0, this is what Lin just proved. If beta is larger than 0, let us say this region is stable, this region is unstable, and this is stable. If we increase beta and it increase after this value, then it is always stable. This is exactly the really criterion. I mean, from the inflection point theorem, this is a critical point. And in the negative, this is also this point. Unstable region is I. All the alpha beta is in I. The linearized equation is unstable. Or the shear flow is unstable. I mean, the shear flow is linearly unstable. So the next part, we mainly talk about the long-term dynamics near a shear flow. For the long-term dynamics near a shear flow, we just recall that it is important to see if there is some non-shear steady state or non-shear traveling wave near the shear flow. In some early work, Hao and Keith, they prove that the linear emissive damping. What do we mean by emissive damping? It means that if we take the initial data is from the a small neighborhood of the shear flow, then the solution will convert to some shear flow near the given shear flow. I mean, the second component of the velocity will convert to 0. Then Hao and Keith, they mainly observed for the quiet flow. The quiet flow is the profile is y, uy is exactly y, and for some kind of monotone flow. And for the mathematical proof or the analytic proof, Lin and Zheng, they prove this for the quiet flow in a channel. And then some groups prove it for the monotone flow, for a class of monotone flow, to extend the quiet flow to a monotone flow. And for non-monotone flow with some symmetry, for example, the flow is even, Wei, Zhang, and Zhao, they also give some proof for the linear image damping. And for beta is not zero, we also prove it for some for some class of flow. So in this work, there is an important assumption is that the linearized operator should have no embedding eigenvalues. Here, the linearized operator is in the form of stream function, and since the essential spectrum is the whole range of U, the whole range of U. If in these works, across for quiet flow, this is an explicit flow. It has the linearized equation has no embedding eigenvalue, and for this general flow, this assumption should be added. I mean the linearized equation, the linear operator does not have an embedding eigenvalue. And in the nonlinear case, Barros Masmodi, Deng Masmodi, and they works on the quiet flow in this region, and they mainly consider the emission damping and the perturbation is taken in some Jabri class. And Deng Masmodi proved their perturbation space is critical. You know, inner school and Jia, Masmodi Zhao, they extend it to monotone flow in a finite channel. But the monotone is not every monotone flow. It has some assumption like this. For more general flows, the nonlinear emission damping is still open and very challenging. So on the other hand, along another line, if the linearized equation, the linear operator have some embedding eigenvalues, then the dynamics near the shear flow will become richer. For example, first we look at the first result by Lin and Zheng. Near quiet flow, as I said before, for quiet flow, the linear equation has no embedding eigenvalues, but if we take the regularity of the perturbation very low, then they find a shear flow near the quiet flow, such that if we linearize the equation near the perturbed shear flow, then the linearized operator has an embedded eigenvalue. From this perturbed shear flow, we use some bifurcation theory to show that there exists non-shear steady states in the low in the space of low regularity, and if the regularity is larger enough, here they give a critical number, and this is the perturbation for the vorticity. The critical number is 3/2. Yeah, I mean, if the regularity is bigger than 3/2, then the phenomena mainly relies on a quiet flow itself. Since it has no embedding eigenvalue, so the result is expected. there are no traveling waves in such a space. And then causal layer, the causal layer and Planetary mass body method, they mainly focus on the low regularity case. If the perturbation is taken in the low regularity case, then they find some new phenomena near the quest flow. For example, they find non-trivial traveling waves, and the traveling speed is of order 1. They find the quasi-periodic solution. These are some new solutions near the shear flow. And for the other shear flow, the first three are for quest flow. For the other shear flow, for example, for the Comer flow, the profile is semi. And if they consider the reading is in square torus, a square torus, then the linearized equation has the zero embedding eigenvalue, so for any perturbation, no matter what regularity is, then there is non-trivial steady state. And if they take the reading is rectangular square, then things become different because the linear operator has no eigenvalue, embedding eigenvalue in this case. And if the regularity is large enough, then they show that there are no traveling, no non-trivial traveling, no non-trivial steady states. And for the posterior flow, the is the profile is y square, and also the linear operator has no embedding value. So they prove that if the regularity is taken large enough, I mean the perturbation space, and then there are not such traveling waves. So the traveling waves or the steady states are mainly constructed by the bifurcation theory. More precisely, the Kondo-Robnowicki bifurcation theory. And in this theory, an important thing is, just as I said, the linearized operator should have some embedding or isolated real eigenvalue. But in the case of beta is zero, then there is no such eigenvalues. There are no isolated real eigenvalues, only possibly embedding eigenvalues. For beta is not zero, we found that there exists some isolated eigenvalues. So by these eigenvalues, we can construct some traveling waves. The traveling waves have some properties which are different from the above one. For the above cation flows, the velocity, the horizontal velocity may change sign, and for the traveling waves, the horizontal velocity cannot be changed sign. Because beta is due to the Coriolis force, so if there is no Earth rotation, so one cannot find such traveling waves with the fluid trajectories moving in one direction. The case size may change some. Yeah, but the isolated eigenvalues, such traveling waves cannot change sign. This is purely due to the Coriolis force. And let us see some analytic thing. So the base term for the Euler equation, for the linearized Euler equation, made some fundamental changes. if we take it in the stream function and after Fourier transform, we will get the linearized Euler operator. Important difference. A difference is if beta is 0, then the isolated real eigenvalue is empty. If beta is not 0, in general, it is not empty. And for the science law, before it exactly exists some isolated eigenvalues. And how do we look at this thing? We can write it in the Rayleigh-Guo equation. If C is an isolated real eigenvalue, if and only if the eigenfunction satisfies the Rayleigh-Guo equation with the Dirichlet boundary condition. And the first eigenvalue can be expressed in the variational form in this case. Now, if beta is larger enough and this term, the potential term, is negative, then the whole term is negative. And if we take the Biot number, so the eigenvalue for the Sturm-Liouville equation and the Biot number, the relation is just like this. So if we take the Biot number as the principal eigenvalue, then we will find for such Biot number, or for such periodic, the isolated eigenvalue, isolated real eigenvalue is not empty. And for a class of shear flow, there is richer dynamics near a shear flow. So the shear flow mainly assume that at the critical point of U, the second derivative of U is not 0. Under some endpoint conditions, now if the critical points, if there is no such point, which is a critical point, at the same time it is a minimal point, then for any beta is positive, there is at most finitely many traveling wave families near the shear flow. If this condition is not true, I mean there is a point which is critical and minimal, then we will, there exists a critical point. Before this critical point, there is at most many traveling wave families, and after this point, there are infinitely many traveling wave families. All of these traveling wave families are due to the isolated real eigenvalues. So the traveling speed is not in the range of U, not in the range of U. And if the profile is degenerate, by the profile is degenerate, I mean that there is a critical point which is a minimal point, and its second derivative is also 0. So we call it a degenerate profile. Therefore, such profile, for any beta is positive, there are infinite many traveling wave families. So let us see if the shear flow is not such, it is not singular, then the dynamics near the shear flow may be simpler, relatively simpler. And if the shear flow is singular, if a little singular, then the dynamics near the shear flow becomes a little complex. And if the shear flow is more and more singular, then the dynamics near the shear flow becomes very complex and even chaotic. So these traveling waves mainly due to the isolated real eigenvalues, and using a bifurcation theory, we can construct such a family of traveling waves. The traveling waves takes this form, takes this form, and it is near the shear flow in this norm. And here, very importantly, C is the traveling speed is not in the range of U. And the second component of velocity is not zero. So this is a non-shear traveling wave. The non-shear traveling wave makes the dynamics near the shear flow more richer. So I skip the details. And how can we find such a critical value? I just explained by this picture. If beta is less than a critical value, then the eigenvalues, there are at most finitely many eigenvalues tend to negative infinity as C tend to actually C convert to U minimum. And if beta is larger than this critical value, then all the eigenvalues will tend to negative infinity. This is mainly because this is mainly due to the optimal Harding inequality. For example, we see such a toy model. We take the flow U is this form, and let us see the energy conservative form. By the optimal Harding inequality, if beta is in this range, then the conservative form is bounded from below. Here, the point is that these two terms competing with each other, and if this one wrong, then we will get finitely many eigenvalues which convert to negative infinity. If this one wrong, then we will get infinitely many one. So the critical point is from the optimal content form. Exactly, if beta is larger than this critical value, then we can take a series of text functions such that the energy conservative form go to negative infinity. So the last thing is about the create flow. For the create flow, if we use the about theory, we only know that there exists at most finitely many wave families near the create flow. But what do we mean by the at most? It means existence or not. So this is what we want to study. Since at most finitely has two means. The first one is non-existence. The second one is there exists some, but it is finite, but the number is finite. The motivation is from the following two cases. For beta is larger. Now we consider beta is larger enough. From about theory, we can see that for some view number, there exists families near the create flow. But from some results from Li and Zheng, we will find that if beta is smaller enough, then for any horizontal periodic, there exists no traveling waves near the shear flow. Here we only consider the regularity is large enough. So we want to determine if we now give a view number, or give a horizontal period, and can we determine for which beta there exists traveling waves, and for which beta there exists no traveling waves. So this is the second question. there is another question, is the first one. The first one is that we only consider the isolated real eigenvalues. It corresponds to the traveling speed lying outside the range of the required flow. And initial question is that if we take the traveling speed inside the range of required flow, I mean inside this interval, and can we find some traveling waves? We mainly discuss these two questions. For the first one, the answer we can get is that if the perturbation is HS, here is the velocity perturbation, space is HS. S is larger than or equal to 5. And for any beta is not 0, then if the traveling speed is in such a smaller interval, not the whole interval, but a smaller interval, then the traveling waves, then there is no such traveling waves. Or in other words, if it is a traveling wave, then it must be a shear flow. So this interval cannot be extended to the whole interval. The reason is that if we take some view number and some Coriolis periodic Coriolis parameter, and there exists some traveling waves with traveling speed really converge into minus and or positive one. So to state the second result and answer the second equation, we first define the principal eigenvalues for the required flow. For the required flow, we know that the profile is y. So here is beta. I mean the second derivative of the OU is 0. And we can show that the minimum can be attained by a finite number. The main reason is that although there is singularity here, for C is equal to -1, but here there is Dirichlet boundary condition. So the singularity can cancel. And this is the reason why the infimum can be attained here by a finite number. And we can and then there is some monotonicity and continuity properties of the eigenvalues. And this is symmetry of the eigenvalues. The result is stated as follows. For the perturbation as we taken before, and now we choose a horizontal period t, and then the view number is chosen. For example, the view number is here, and now we draw a horizontal line. It intersects a point with the curve. This curve is the minus of the first principal eigenvalue curve. So we have an intersection point, and after this point, there exists traveling wave families, and before this point, there exists no traveling wave families. In other words, we give a critical point such that if the alpha beta is in this region, the existence is not true. And if alpha beta is in these two regions, then there exists traveling waves and at most finite manner one. This is the main result. And for the proof, the main idea is that if we fix beta, now let's see, run from -1 to -infinity, then the spectrum will fill such a line, will fill such a line, and there are no spectrum in this region. Okay. This is the last one. So the last one is to consider if there is some richer dynamics near the shear flow. If we consider the regularity is low enough, the result is similar as Lin and Zheng. If beta is not zero, I mean, Lin and Zheng prove this for beta is zero, and we just extend it to the case beta is not zero. Although the result is the same, but the extension is somewhat non-trivial, since there is some singularity things to be handled. So let us give the precise result for any horizontal period, and if the perturbation space is taken to HS, then for any epsilon larger than 0, we can find steady states near the quiet flow, and the second component of the velocity is not 0. In other words, it is a non-shear steady state, and so that the long-term dynamics near the shear flow is exactly richer. Yeah. Thank you for your attention.